Thanks. Our next speaker this afternoon is Yee Whye, who's going to talk about some Bayesian hierarchical models.
Okay. Thanks, Chris. Okay, so the title is Bayesian Hierarchical Community Discovery, and this is a joint work with Charles Blundell back when he was a grad student with me, when we were both at the Gatsby unit at UCL. I'm now at Oxford, and also a bit of DeepMind, and Charles is at DeepMind. Okay, cool. Right, so what we'd like to do here is to kind of look into ways in which we could construct community structure that looks like this, where the communities are kind of form a hierarchy with kind of communities and sub-communities within each community. And we're thinking about this hierarchical community structure as basically some sort of hierarchical partitioning of the nodes of our graph. Okay. And the way we're going to approach this is by using a model-based approach. So that's the Bayesian part coming in. But at the same time, we'd like to kind of approach this from quite a computational perspective and think about how can we design our model in such a way that it kind of makes sense from a kind of computational efficiency perspective. Okay. So I guess we took more of a pragmatic Bayesian perspective where we actually designed our model in such a way that the computations work out well, okay? Rather than designing our model with proper priors, subjective priors coming from expert knowledge. Okay, right. So here's a summary of the talk, I guess. So the proposal here is we want to come up with a method for discovering hierarchical community structure in social networks. And as I said, the hierarchical community structure is kind of basically it's going to look like basically these tree structured mixture models, okay, where each mixture component you can think of as a stochastic block model, and there's actually going to be exponentially many such type of stochastic block models within our hierarchy. And the way we're going to construct our hierarchy is actually via a model-based greedy agglomerative clustering algorithm, which implements some sort of Bayesian model selection. So the time complexity here is actually still n squared, which is kind of unfortunate. We but actually in practice it seems to work really well. But if I have time, I can kind of just give the example of what happens to cause this worst case complexity. Okay, so I'll start with a stochastic block model, as everybody here is familiar with. So this assumes that our nodes of our graph is partitioned into a number of blocks, and basically the distribution which we're going to use to model our interaction matrix is basically that we can decompose this probability of observed interactions as a product over pairs of blocks, right? And for each pair of blocks PQ coming from our partition, we have some parameter theta PQ, which tells us the probability of an H connecting a pair of, the probability of an H connecting a pair of nodes in that block of P and Q, and 1 minus theta PQ is simply the probability of no H connecting a pair of nodes in that pair of blocks. Okay. Right. And so if we place a beta prior on this theta parameter, and we can use different beta priors for the on-diagonal and the off-diagonal blocks, then that basically leads us to a marginal probability of our data given our partition phi, okay, which is basically we have the on-diagonal blocks. So that's basically given by this ratio of beta functions. And we have a bunch of terms, one for each pair of off-diagonal blocks, and again that's a ratio of betas. Okay, and in the following, what we'll do is I'll write basically f for this, basically a ratio of betas, and g for that ratio of betas. Okay, so there are 4 hyperparameters here for alpha, beta, delta, and lambda, and basically these are chosen to be assortative. So basically, the probability of two nodes in the same block being connected is higher than two nodes in different blocks. Okay. And in general, of course, we can generalize this to other kind of exponential families with conjugate priors. All we need to do is to be able to calculate the sufficient statistics of the pairs of nodes in each block or each pair of blocks, and we can calculate some function for that, which tells us the marginal probability of the data for that pair of blocks. Okay. Right. Okay. So so this is one way of kind of treating a stochastic block model in which we have one parameter basically for each pair of off-diagonal blocks. Okay. Another possibility which we could take is to say that we're going to use one block, basically one of these terms, which captures all the off-diagonal interactions. Okay, so we have a product over the probability of the data within each block. Okay, and those we assume has higher probability of interaction a priori, and then times the probability of everything else. And basically, we're just using one single beta parameter for all the off-diagonal block entries. Okay, it might be useful to just draw on the whiteboard what I mean by this. So basically, if we have blocks which look like this, then we have f terms for each of this. Okay, so basically we have one parameter for each of these blocks, and then we have a g term for everything else, basically. Okay, and both of these are functions of the sufficient statistics coming from the from each block and for everything else. And in terms of so if you'd like to estimate the block structure, then we'll need to kind of place priors over partitions of our nodes. So there's a few possibilities here. We could take a parametric approach where we use a finite Dirichlet multinomial partition, or we could take a Bayesian non-parametric approach and use something like a Chinese restaurant process, which leads to something called the infinite relational model in the machine learning literature. Okay. And then in terms of posterior approximation, there's a whole bunch of things you could use. You could do MCMC sampling over the space of partitions. You could do variational Bayes, or you could do map. Basically, we want to maximize to find the partition that has highest posterior probability given our data. Okay. So I guess I'm kind of introducing this as a way of introducing the notation which I'm going to be using here, basically this f and g notation. So think of the f and the g's as likelihood terms associated with on-diagonal blocks and off-diagonal data. Okay. Right, so that's a stochastic block model, and the issue that we would like to address in this talk is having to do with generalizing from this flat partitioning sort of idea to a hierarchical partitioning idea, okay, and trying to do this in a computationally efficient way. Okay, so this is, I guess, probably the most important slide in this talk. It's actually the talk is very simple, so I can actually go into quite a bit of detail about the model and the algorithm, and basically this describes the model. Okay, so let's suppose that we are given a hierarchy. Okay, so that's our hierarchy here. And what I said previously was that we're going to think about this hierarchy as a mixture of stochastic block models. Okay. And it's a mixture where each component of the mixture is a particular stochastic block model with a particular partition on our space. And basically, these are the components of the mixture. And we can think of this as, so for this tree, this is a partition in which everything falls into its own block, into one single block. Okay. And this is a partition in which AB forms one block, and CDE forms another block, and F forms its own block. And then this would be a case where A and B are separated, and then this would be a case where CDE are separated, and this is where everybody is in their own block. Okay. And basically, this mixture model is constructed as follows. So we can think of this. So these are the probabilities for the partitions in this mixture model, And the probabilities are constructed as follows. Basically, we imagine that we start at the root of this hierarchy, and we make a decision whether we are going to keep everything under the leaves at that point of the hierarchy together in a single block with probability pi, or we're going to split this hierarchy into its 3 children and then stop there. Okay, so that would be, this would be the probability of deciding not to stop at the top of the tree and then deciding to stop for this subtree and for that subtree. Okay, and then this would be the probability that we decide not to stop at the top and then to not to stop here and then stop here. So that's 1 minus pi squared times pi, and then similarly for here and for here. Okay, so that, yes?
Have you fixed a random permutation?
The ordering doesn't matter. The ordering is just so that we can visualize the hierarchy. Okay, so it's actually independent of the ordering, but the model is actually not projective, if you're asking about that. Okay, right. In general, we're going to allow this probability of stopping at each level of the hierarchy to be dependent on the node of the hierarchy. Okay, so that gives us actually the probability of a particular partition under our tree, where the pi's are now going to be dependent on the node. Okay. Basically, we can think of this as basically this is the probability of basically. So we can basically think of a partition as taking the tree and then pruning off some bits of it, and basically this part here is the probability of not stopping at each internal node of that reduced tree, and this is the probability of stopping at each of the kind of the leaves of this reduced tree. Okay. Right. So that's the prior over partitions. I'd like to define the data kind of observation model as well. Okay, and it's actually quite similar to what we had previously for the stochastic block model. So if you have a single block, then we simply have a f function. Okay, so that's simply the probability of all the interactions under that block. In this case here, we have 3 blocks, so f, f, and f, and then we have a single g, which is the probability of all the off-block diagonal interactions, and we assume that this interactions a priori has lower probability of happening. This is where the thing is a bit weird. So here what we did was, so we had this block here which consists of A and B, and we split it into further into 2 sub-blocks of A and B, right? So here we've kind of constructed another split here, and we have F and F, and I'm going to have another G here. Okay, so the idea here is that when we think about this partition, we still have this notion that the 2 nodes A and B are still more related to each other than they are to, for example, nodes outside of A and B. So A is still more related to B than A it is to C or D or E or F. Okay, which is why we use this separate G function. But another reason why we chose to do it like this is so that actually we can compute efficiently in a recursive manner the probability of the observations underneath the tree. Okay, and we can do this quite easily here. So we can basically think of this as, this is the probability of not splitting at the top of the tree, and that will be the probability of the observations underneath that kind of coarse partition. And this is the probability of splitting at the root of the tree, and then this term here has to do with the probability of all the off-block diagonal data, and this is just computed recursively. Okay, and this can be computed efficiently. Basically, you just have to compute the probability of the data underneath the tree. We just have to compute each of this in a recursive manner, starting from the bottom of the tree and working our way upwards. Okay. So both the f and the g functions are functions of the sufficient statistics of the data either in the on-diagonal blocks or the off-diagonal blocks. So where theta ss is basically the sufficient statistics of the leaves of a kind of a cluster of nodes S. Okay, while sigma ss not ch. So what this thing is, I guess, not children. I guess this is just the off-block diagonal entries of our data matrix. Okay, right. So that's the model. Is there any questions about this? Nope. Okay. Cool. Right. So the way we designed the model, and particularly the way we kind of constructed this G's in this kind of funny way is so that we can compute this this data probability underneath the tree efficiently. The next question is how do we learn the tree given some data? Okay, and the way we're going to do that is basically using a greedy agglomerative clustering algorithm, where initially we start with each node in its own tree, and then we basically recursively pick a pair of trees to merge, which maximizes some local base factor, okay, score, and then we merge that pair of trees, and then we just so now we have one less trees than before, and we just repeat this, and so this repetition will run for n-1 iterations, and then at that point all the data is kind of collected into one single tree, and then we stop. Okay. Turns out that the computational cost for this algorithm is actually order n squared log n, and this has to be done with some quite smart way of caching our computations. If you just do this naively, it will be like order probably n to the 4, I think. Okay. Right, and the local base factor that we use is basically of this form. So if we pick two trees, I and j, and we decide to merge them, okay, then the score for that merger is basically the probability of the data under the merged tree, okay, divided by the probability of the data without merging. Okay, so and we have to have an additional g term here to account for the fact that so p of dii. So I forgot to introduce this notation, but basically dmm is basically the data underneath the tree m. Okay, so so for example over here, dab is simply that block of observations here, okay, and dcde is simply this tree by tree block. Okay, right. So okay, so we can compute this dmm, so probability of the data under tree m according to this recursive rule. We can also compute the probability of the data under tree I and the probability of the data under tree j. Okay, but we need an additional term here to account for the data which isn't accounted by basically the ith tree or the jth tree, basically the kind of the data at the kind of that's outside these two trees. So if it's something like so that's I and that's j, and that's your g of sigma ij. Okay. Right. Okay. So and we considered two different ways of merging trees. Okay. So if you have trees I and j, then the obvious way of merging them is basically by this is what we call a join, which is basically that the two trees I and j are basically subtrees of the tree m. Okay. We also considered a possibility where tree j is absorbed into tree I, where now the tree j is actually turned into a subtree of tree I. Okay. Or we could have I being absorbed into j as well. Okay. So this allows us to produce potentially non-binary trees, and we are going to choose our this pi probabilities according to a particular form, which I won't really kind of explain, but basically it allows the model to prefer a simpler non-binary tree if there is no structure in the data. Okay. Okay. Cool. Right. So coming back to the algorithm. So that's it. So we start off with all the nodes in its own tree. For each pair, we compute the score, and then we basically pick the pair of trees with the highest score, and we just merge them and we repeat. Okay. So I said previously that we have to do a bit of smart caching, because if you don't do this, then the computational cost is kind of higher. It's either cubic or quadratic or n to the 4. I guess I'm kind of running out of time, so I won't really go into detail, but you can do this efficiently. Okay. Okay. So I'd like to kind of mention two other ideas that we also used. One is that at each point of this algorithm, at each iteration of the algorithm, there could be many potential mergers that have equal maximal score. So for example, at the beginning of the algorithm, each tree is just a single node. So basically, a pair of trees basically corresponds to a pair of nodes, and that pair of nodes either has a connection or it doesn't have a connection. We've constructed our prior in such a way that the pairs of nodes with a connection has a higher score than pairs of nodes without a connection. But then there are still lots of pairs of nodes with a connection. So which one do you pick? Basically, what we ended up doing is that we simply, at each stage, we pick one of these pairs of nodes, pairs of trees with maximal scores uniformly at random, and we just merge them. So basically, if we run this algorithm, we're going to get a random kind of tree out, and we just repeat this multiple times, like what you do in things like a random forest. Okay. So you can kind of repeat this multiple times to get an idea of uncertainty over the hierarchies. And also, actually, if you average over the predictions from these multiple trees, that we can show that improves the performance significantly. Okay. Right. The other thing that we did was actually for sparse networks. So if you have, particularly because we want this to be a kind of a community discovery algorithm, if you have two trees for which there's no connection between any nodes across the two trees, then there's no point of merging them because there's no connections, right? So basically, we only consider pairs of trees to merge only if the two trees are connected by at least one edge. Okay. So this encodes the assumption that communities are connected sets of nodes. And it also significantly reduces computational cost as well. Okay. So in terms of time complexity comparisons against other, I guess a lot of these are Bayesian non-parametric models. So we have the infinite relational model. This is a naive implementation versus a sparse implementation. We have a latent factor relational model. This is based on the Indian buffet process, and there's kind of a whole bunch of other ones here. And generally, most of this actually have a computational cost that is quadratic in the number of nodes of our network, and typically also quadratic in the number of communities or factors that you want to discover. R here is basically the number of restarts, and I is the number of iterations if it's an MCMC sampling algorithm. Okay, so compared to this, BHCD tends to be quite efficient. Basically, instead of a k-squared I term, basically it's a one-pass algorithm. We just have a log n factor. Okay. Okay. So I think this might be the first occurrence of Samson's monastery today. But really, I showed this figure because I'd like to just kind of show you the difference between a non-binary tree that's discovered using this method versus a binary one. So the binary one here that we have is basically one where we only consider the join operations rather than the absorb operations. Okay. You can see that in this case here we have a bunch of, so in this case we have a flat subtree, okay, which basically says that there's no, we can think of this as that there's no kind of additional structure within this collection of monks once they are in their own block. Okay. While if you do a binary hierarchical clustering, then you get this sort of structure which actually doesn't mean anything. Okay. Right. Okay. So I'd like to just show you a few kind of just one more example, and that's it. So this is a NIPS co-authorships of data sets. Basically, we have authors in NIPS proceedings from over about 17 years, I think, in this case. And two authors are linked if they co-author a paper together. Okay. In this case, and then we kind of constructed our kind of hierarchical partitioning, and we only show the top of this tree. Okay, and it's actually quite actually for about half of the basically underneath each of this there's a list of names of authors. Basically it's just I think listed by kind of popularity, basically the number of papers that they authored. Okay. So most of this kind of communities I don't really know, but about half of them you can kind of see where it comes from. So this community, for example, is basically the community of MIT faculty, I think. This here is basically the AT&T Bell Labs people. So this one is here is UCSD, interestingly. This one I think is not actually based on coming from a single university, but rather is people working in reinforcement learning. And then this one here is kernel methods. Okay. So it's kind of about half the communities is interpretable. The other half is not that they are not interpretable, it's that they are neuroscience authors that I don't know about, so I can't actually interpret it. Okay, so that zooms in a bit, I guess. Yeah. So okay, so we compared it against the infinite relational model. We also compared it against the ILA model and the LFRM model as well. Basically, it works just as well as the kind of infinite factor models and works better than the infinite relational models in general. Okay. So here we compared the infinite relational model with inference done using MCMC or greedy, basically map, approximate map. And we compared actually four different versions of BHCD. So the original one versus the sparse one, where we only consider a pair of trees to merge if there's at least one edge connecting them, and we also considered either only using binary trees or rows trees. Okay. And on this plot here, we looked at basically the average log predictive of held out test edges, and this is repeated average over 10 runs. Basically, is 10 times cross validation. And this is basically the runtime in seconds. This is a C implementation. And you can see that it's actually significantly more efficient than the infinite relational models. And it produces also just as good average log predictive scores, particularly in the non-sparse case. So the sparse case is faster, but it didn't get as good a result. Here we also looked at kind of accuracy, test accuracy, and area under the ROC curve, and we always see that basically the BHCD curves are to the top and to the left of the infinite relational model curves. So basically, it's faster and it is sometimes even more accurate, like this case. Okay, so that's it. So what we've proposed here is basically an efficient Bayesian model-based procedure for discovering communities. We thought quite a lot about how do we make this model, this method computationally efficient, but there's still lots to do. So unfortunately, Charles, after this project finished up, and then he went off to DeepMind to do other great stuff, but I don't have anybody to work with. Thank you.
Questions?
Zeke. Oh, sorry. In the hierarchy, is there a length to an edge?
No, there's no length to the edge.
I guess it makes it a little bit hard to interpret the NIPS tree because
Right, yeah.
the model has no ability to, I don't know.
Yeah, it's true. Would be interesting to think about how do you kind of
Probably
incorporate.
break your dynamic program now.
Yeah,
And
it
I
might
guess
be possible.
another obvious question, I mean, to a machine learning audience, I guess they would ask, okay, how about, what are the comparisons to like the latent feature relational model look like? Or did you do that? Did I miss that? Did you compare?
It's not reported here, but we did compare, and generally they produce similar accuracies and log predictives and stuff. Because
I'm not sure that I captured everything, so it sounded very interesting. So I asked myself the question, could you apply your method to community detection? Because there's reminds me of the Newman-Gilman algorithm, which is also a greedy algorithm, or many greedy algorithms for community detection, where you also merge according to some score. But then you have an additional layer where you decide which is the optimal partition.
Right, yeah. So
You have an optimality criteria.
you could do that as well, actually. So in fact, if you look at this score here, if you find that your score is below 1, then you could stop. Basically, that's kind of is a model selection sort of thing. So, do you prefer these two communities to be merged or not? According to base factors of computation, that's possible too.
Do you have once you've got your partition, do you have an overall score which you would then calculate?
For the whole thing?
Yeah.
Yeah, you can come up with that. Yes. Yeah. We just did this kind of locally because we want the computations to be efficient.
I was just going to say, though, I mean, communities are sort of a fiction. So, I mean, in some sense, I think hierarchies are often a better description of the structure that's going on. So it's funny to take something that has more structure and then
right,
for something.
and then kind of flatten it. Yeah. True.
Hierarchies are a fiction too.
Oh,
Yeah.
oh, yeah, for sure.
Everything is a fiction.
Okay, and on that note.
Thank you.